Hey, today we are going to revisit an old friend. Last year in calculus, we learned how to find an arc length. To do this, we use parametric equations. And if you need to, there's a great video series I did on that, so go and take a look at that. That's why we use parametrics instead. And we had a formula for this where S was the arc length from A to B, and we multiplied that, and that was of the square root of x prime of t, quantity squared, plus y prime of t, quantity squared, dt. Now, we can shorten this a little bit because we can remember that the square root of x prime of t squared plus y prime of t squared is just the magnitude of r prime of t. So we can kind of write this another way if we like. And just another way to do that. We'll talk about that in a second. We can apply this to three-dimensional equations as well. For example, if in 3 dimensions we would get x prime of t squared plus y prime of t squared, we just add the third variable, z prime of t squared. Don't forget your dt, your differential. So arc length can also be, and if I apply my same rule here with the square root of x prime of t squared plus y prime of t squared plus z prime of t squared, that's just going to equal the magnitude. We can rewrite our arc length using this formula, where, again, the magnitude of r prime of t is just the square root of x prime of t squared plus y prime of t squared plus z prime of t squared, right there. Either formula is acceptable to use. So let's take a look at an example. Now, I'll be honest with you, in most cases, if they're not circled, you're probably going to have to use a calculator for this. I am using my TI Nspire, because I rock. Okay, so if we want to determine the length of this curve, that's, again, talking, of course, about arc length, we are going to need, of course, r prime of t. So let's go and take the derivative. Now, by the way, we should remember this shape right here. This is, ignoring the x, this is a circle on the yz plane, but we are coming out on the x. So it's a spiral, spiraling out on the x-axis, in the x direction there. So this is our spiral right here, or helix. And this becomes, when you take the derivative, 2, this becomes 6 cosine 2t, and this becomes negative 6 sine 2t. And there's our derivative. To find the arc length between 0 and pi, it's already in terms of t. So to get my arc length, s, is going to be the integral from 0 to 2 pi. I'm going to square these. This becomes 4 plus 36 cosine squared of 2t plus 36 sine squared of 2t. Don't forget your dt. And notice, I'm going to zoom in here a little bit. Notice this part right here, we should recognize this already. That is just cosine squared plus sine squared, which is 1. We're just multiplying it by 36. So my integral just becomes 0 to 2 pi, the square root of 40 dt. Not a circle. That's a lot nastier. We'll see an example later on when we really can't solve this by hand. But this one we can. This just becomes the square root of 40t. So we're going to have to review the FTC if we need to. Remember the fundamental theorem of calculus. The FTC says if we're taking an integral from a to b of f prime of x dx, that becomes f of b minus the value f of a. So that's what we're doing here. So we took the antiderivative. We get the square root of 40 times t. I should write that a little bit better. The square root of 40 times t, and we're going to evaluate that from 0 to 2 pi. So this becomes the square root of 40 times 2 pi minus the square root of 40 times 0, which is just 2 pi root 40. And this is the length of that spiral for that time. Right there. And remember, if this is our spiral, let's see what it kind of looks like right here. Sometimes it helps to kind of see it. If here's our spiral, ready? We can even find out where we're starting at 0. If I let everything be 0. Ready? At t equals 0. Let's find out where we're starting. At t equals 0, we're at the point 0. Sine of 0 is 0, 3. So let's see here. So we are at 0 on the x, 0 on the y, up 3 on the z. And remember, it's going to be kind of hard. I'm spiraling out on the x here. So you can kind of imagine us spiraling out on the x until t equals 2 pi. So the length of that bit of spiral is just 2 pi times the square root of 40. Right there. I'll be honest with you, I'm impressed with my spiral. Nice. Now, we can go a step further and convert our integral expression for the arc length of the curve into an arc length function. So, in this case right here, we can set s, so now it becomes more of a function for us, where the integral goes from 0 to t, r prime of t of u du. Notice where t is just a variable. This might look familiar, like your second FTC. We saw that a lot when we did our second FTC right there. So if I wanted to determine the arc length function for this equation right here, ready? I can use my little rule right here. Now remember, this right here, this is our magnitude, right? That's our little formula up here. So to determine the arc length, again, this is a spiral. I would need r prime of t, which is not too bad, negative sine t, cosine t, 2. There's r prime of t. To get the length of my curve, remember we want to write it as a formula right here, we would go from 0 to t, the square root of, square this, sine squared t plus cosine squared of t plus 4, don't forget your dt, and this just becomes from 0 to t, the square root of, now recall, this is just a number 1, so we get the square root of 5 dt. And in solving this, we would get the square root of 5 t, and we evaluate that from 0 to t. Of course, that's the square root of 5 t. So what this is telling us, what this tells us is to get the length at any given time t, it's just going to be the square root of 5 times t. So this will give us the length at any t value. Alright, and if you go to video 2, we'll take a look at a couple more examples using these formulas.